Hey there, everybody. We'll go ahead and let people start coming into the Zoom room here. As you get settled in, I'd love to direct you to the bottom of your Zoom window where you'll see a little chat icon. Go ahead and click that, and we're going to practice how you will answer or ask us all of your questions today. When you click the chat bubble, it should populate a little chat box in the bottom right of your Zoom window. When you type into that chat box, make sure the to is set to everyone. That's because Tom and I will be answering questions in the chat box today, and we don't want to look like we're talking to ourselves. So make sure your question is directed to everybody so we all know who has asked what and why we're answering the questions that we are. That being said, go ahead and click into that chat box and let us know what your plans are this holiday season. Are you a order dinner in and watch movies type of person? Maybe something an interesting snowy experiment you're doing with your students. I'd love to hear more. So go ahead and chat and make sure that chat is set to everyone and just let us know what your holiday plans are. I know I am heading up to Seattle, so that's about 3 hours north of where our office is, and just going to do a little Pacific Northwest holiday. So, what's everyone else up to? Let's see. Oh, we've got somebody heading to Whidbey Island. Very nice. Very nice. Let's see. Family here. Awesome. Yeah, we're probably all approaching winter break. So congratulations, educators. You're almost to a little break there. And it looks like it is 4 o'clock. So while we probably have a few people still filtering into the Zoom room, I do just want to cover some housekeeping items. So we'll jump right into that. And then I'll pass you off to our fabulous presenter today. First and foremost, a recording of today's webinar will be live on both our website and our YouTube channel. It usually takes us about 3 to 5 business days to get that edited and uploaded, so keep an eye out for that. It's coming, but it does just kind of take a couple days to get it ready. As soon as it's ready, we will email that to you, so keep an eye on your inbox. In that email, we're also going to include a resources folder. Within that folder, you can access a truss experiment, as well as today's presentation with clickable links. I'm going to drop that link in the chat as soon as I'm done talking. And then you can also access that. If you need that, please feel free to let us know in the chat, and I'd be happy to drop the link back in. And the last thing I wanted to mention to you all is that we want to answer your questions. So please, if you have a question about anything, drop it in that chat box. Make sure the to section is set to everyone. Like I said, that just keeps us looking like we're talking to real people and not ourselves. And that being said, we'll hop into today's presentation. Thank you all.
Thanks, Dylan. Tom Smith here. You get me twice. Sorry about that. So I'm a part of the physics and engineering education team here at Vernier, and I've been with Vernier for 10 years. Before that, I taught high school engineering and physics at a local high school here in the Portland area. Was in the classroom for about 9 years before joining Vernier. So that's my introduction. A lot of you sent in questions before the webinar, which is great. I kind of synthesized them as best I could, put them in this slide. Hopefully we're going to get to all of these questions and through the course of the webinar. I do have these kind of summarized again at the end in case I skip over them. There are some questions that I'm not the expert of, and so I'll be crowdsourcing answers to some of those questions as we get to that point. I will also note that I ran through this webinar earlier today, and what I have planned is a bit more than the 30 minutes advertised. So if you need to drop off, just know that you'll get a link to the webinar. You can watch it later if you need to scoot out to go grab some dinner or take care of kids or whatever it is you need to do. So we'll come back to those questions again throughout the webinar. Okay, so bridge competitions are just great fun activities. They're some of the more memorable things that I did in the classroom. This is a picture of one of my AP physics classes where we took a trip down to Oregon State to be part of a regional bridge competition that was a feeder to the Illinois Institute of Technology competition. We, you know, everybody's a little bit different when it comes to bridge competitions. We did some testing in class, but often the regional competition was the one place where my students were able to go and test their bridges. And I didn't have the luxury of time to spend a whole lot of time coaching my kids. In fact, I would spend probably a day kind of giving them information and giving them supplies, sending them home to build their bridges on their own time. I think I was optimistic that they had more time, you know, than I had in my classroom, but nevertheless, that's how I ran it. What we're going to be going through today is a little bit more involved. So if you have the luxury of some time, or maybe an after-school activity where you could engage your kids on a regular basis, that would be kind of the optimum situation. So that's where we're going. Starting with the end in mind, we'll talk a little bit about how to kind of prep your students thinking about bridge competitions. And then we'll talk a little bit about the elements of a bridge, how you might introduce beams and trusses, and then actually building bridges, some tips for passing on to your students about how to do that well. And we'll talk a little bit about the engineering cycle, that plan, do, check, act, and do it again type cycle. So that's kind of where we're going. A couple of times when I started introducing the bridge competition, whether I was doing it in my classroom or down at Oregon State, we took a field trip to downtown Portland and walked along the riverfront and just observed bridges. We just went and looked at the truss designs and tried to understand how those trusses were distributing forces and whether they were in compression or tension, the different members, and just to kind of engage my students. And if I didn't have the luxury of taking a field trip that particular year, we usually went into the gym and looked up at the ceiling in the gym, and there were exposed trusses up there and talked about how they work to distribute forces and support the roof. So if you can find that opportunity to just kind of engage your students up front so they have some inkling of why they might build a truss bridge rather than just a plank, that's a great place to start, I think. Whoops, there we go. So if you do have the luxury of time, a great place to start is just looking at a study of beams. And you might start with just a rectangular beam and think about how its dimensions affect its flexibility. So if you try to bend it this way, not so flexible. If you bend it this way, pretty darn flexible. And what are the differences between, you know, a skinny plank and a thick plank, thick plank and a skinny plank? I guess, yeah, skinny two ways. And then also how long that member is. Is it really long, or is it just a really short span that's being supported along that plank? So really simple investigation. You know, I did it primarily with the just in my classroom with just some wood that I would hand out to my students. Again, I didn't spend a lot of time building a lot of knowledge. There could have been much more teaching involved, but it was a good introduction nonetheless. The next stage along those same lines for beams is just looking at how a beam is constructed. Are you going to use like a box beam, or are you going to use an I-beam? Now, this is somewhat fanciful to think that I'm going to build a balsa or basswood bridge with an I-beam built into it. Maybe a student will do that. But just to look at how that distribution of the wood that you're using affects that, again, that flexibility, that stiffness that is important to the structure of the bridge. And you might even ask yourself and your students, why is that stiffness or flexibility important? And it really has to do with how much stress you're putting on joints. If things are moving a lot, your joints are going to be much more affected by that motion and by that flexibility. Okay, so moving on to the next point here are trusses. So the investigation for trusses, a lot of these investigations are outlined in our From Beams to Bridges activity book. And I think this is the activity that's actually included in the material for this particular webinar. So you can download that if you don't have access to that book. But basically has students look at how that angle of that truss affects its strength characteristics. And the notion of that is that you're going to build a series of trusses and take them to failure, break them, and then just evaluate both the strength and also how they are broken. So I'm going to change camera views here for a moment, and we can look at our structures materials tester. I have this set up with our truss testing accessory on the back of it. And this is a simple triangular truss, probably represented by this medium angled version there. And you can see it's supported on the corners. And then the this bottom section is going to withstand whatever forces we put on it, and we're just going to be breaking the triangular truss. And just for fun, I'm actually just going to break that, just so we have a little bit of interaction during this. And I'll go ahead and collect some data, and we'll take a look at how it breaks. So I'm just applying a downward force on the top of that truss. You can see the force coming in on graphical analysis, and I'm looking at the truss to see where I might be getting some failure. And when I first did this, I was really pretty surprised about how it broke. Oh, now that's unfortunate. What I'm seeing is that this part is just pushing out sideways. So that's my failure in this case. Typically, what I would see would be something more like this, where the one of the members of the triangle actually buckles, and it just finds a weak point in there and pops out. In this case, I have, let me get back to another camera view if I can. I have, you know, this portion, that's the bottom portion of the truss, and these triangular corner brackets are designed so that the truss just pushes out on them. You can kind of see that. If I put a truss in the corner brackets, the tester just pushes down on the top. And these are designed as just blocks to keep the ends from pushing out. My glue failed though, so over time, you might have to rebuild some of these. At any rate, this shows results of 3 different trusses, a fairly shallow one, a medium one, and a steep one. And interestingly enough, the short truss held the most force. And buckling happened, you think about the forces being applied, really pushed out a lot on that horizontal direction until finally a weakness was found in the member itself and it buckled, probably just due to some sort of imperfection in the material. So I'll let you ponder on the nature of that relationship. But it's a good thing to have your students realize just how a truss breaks and what they might do to reinforce that truss to make it stronger. And something that comes to mind for me is I might include some sort of a brace that pushes back kind of mid-span on that those angular members there. Okay, so let's move on to bridges now. So as I mentioned before, the competition that I typically followed was the Illinois Institute of Technology's International Bridge Competition, of which they had regional competitions around the country, and then winners of that regional competition would go to the national or the international competition sometime in the spring. That was convenient because they have set up a series of rules that have been kind of time tested. And although they vary from year to year, they're very similar in their nature. So it's a good place to start. Those particular rules had dimensions based on their test fixture that they were using. Also had used efficiency as the measurement of success. So it's kind of like how much weight did it hold compared to the weight of the bridge. And then specified the type of material that could be used. And typically that competition includes a maximum displacement. So if you have a bridge that is bending but doesn't actually fail, at some point they call it a failure when it bends so much that it's no longer effectively acting like a bridge. Whether you have the time to incorporate testing beams or trusses beforehand, it's always good to reinforce the idea of using those lessons about what a truss does and how um, how a beam might strengthen or become how a stiff beam might help out a bridge and incorporate those into the design. I typically required one-to-one scale drawings so that students could use those to actually build their bridge. So they'd bring their design in. I'd help them make sure that it met the specifications of the rules. And then they would use that to build each side of their bridge and marry it together. With some of my advanced placement classes, I actually had them do a force evaluation of the different members involved in the bridge. And somebody had asked earlier about design software that you could, model your bridge before you actually build it. I don't have a lot of experience with that. When I was in the classroom, I used what was then called the West Point Bridge Builder software. I Googled it today and found this, the Bridge Designer. It was last updated in 2016. and they have versions for Windows and Mac computers. There may be some, you know, uh, compatibility with newer operating systems. I don't know about that, but that's one thing. If you know of other tools that you've used for kind of testing out your design before you build it, I'd encourage you to drop those in the chat just to share them with others, and I'll try to make note of that to share that with others later on in the session. And this happens to be the bridge that I built in preparation for this, so we'll get a chance to break that a little bit later on. Hopefully it'll be a little bit more dramatic than my truss example there, so we'll check that out. Okay, so talking a little bit about building the bridges themselves. Again, I made many missteps. I'll just tell you that right now when I started building this bridge. So, but one of the things that I did that I appreciate was that I laid out my design, I made a copy of it, and then I was able to build both sides of the bridge at the same time. I just put a strip of wood down the middle to kind of brace up so I could push against it and glue my joints and so forth. But I also went stepwise. I just, added a few members, glued them in place, made sure that the glue was able to dry completely. And, occasionally the glue would stick to the paper. I'd just take a razor blade and trim it off, or a X-Acto knife or something like that, and scrape that off. So I could continue to build it step by step. That was the luxury of having time to do this. I think I built it over the course of a week, just doing, 15 minutes or 30 minutes at a time, every day or every other day, something like that. Joints are very important. Somebody asked about how to get good glue joints, and for me, first of all, building it flat on the surface was very helpful, so that I could I could put pins in place to apply a little bit of pressure to keep things tight and allow the glue to dry. Again, not gluing a whole bunch of things all at once, hoping it was going to stay together. You'll notice I also put little braces along the way to, if I had a member that was sitting on top of another member, a lap joint instead of a butt joint. This is not necessarily a gusset, but it does provide a little bit more strength, a little bit something more to push against. Whenever possible, I like to build just in a column. So here's my base. I have a piece of wood laying on that base and another piece of wood laying on top of it, so that when I'm pushing down on the top of my structure, that force is going straight through part to part. If that's not possible, then I'm going to use a lap joint. And that lap joint would be where I'm laying a piece of wood, where's my camera, up against another piece of wood. So not on top of it, but next to it. I'm going to want a lot of surface and a lot of good glue contact on a lap joint like that, as opposed to a butt joint, which is a little bit stronger in my opinion. Gussets are also an option. Some competitions that I've paid attention to prohibit them, some encourage them, but basically it's a piece of material that you would cover a butt joint with in order to just give it a little bit more strength. And if you take a walk and look at bridges, you'll notice like a steel bridge will have like a metal gusset that's riveted onto two pieces to kind of hold them together. So a pretty common use in bridge construction. One of the things that, again, well, maybe not again. I'll confess that I'm not the best bridge builder in the world, but I've talked to some really fine bridge builders. And one of the things they noted is that, you go through that evaluation of a beam, much stronger, much stiffer standing on edge than on end like that. So, but how high do you need to build it? If you double the height of beam, you're basically increasing the stiffness by a factor of 8. Do you really need it that much stiffer, or could you perhaps just add a half of you know, half of a height additional in order to get almost, between 3 and 4 times the stiffness? And I've talked to teachers who have encouraged their students to take a plane and just shave off half of that second laminated piece of wood in order to minimize the weight, but still get that extra strength involved. So a tip for those students and teachers that want to get that highest efficiency when it comes to bridge building. Symmetry is so very important. In fact, when I built this bridge, even after using the tips that I made to try to get everything as symmetric as possible, I ended up with one side of my bridge just a little bit lower than the other side. And when I realized that, I actually braced up that low side so that they were pretty much level by the time I was testing it. And I'll talk more about that in a minute. But one of the things that I used this time around was a piece of styrofoam. You can find a more environmentally friendly material, but I happen to have this at home. Looked about the right size, so I brought it in, and I just basically sandwiched my two sides with that styrofoam in the middle and put some nails through it to hold it in place, and then taped the sides. As you can see, I just used some painter's tape. And that allowed me to get started with marrying the two sides of the bridge together. And as I mentioned before, that I didn't do a perfect job with that, but that got me further along than I had been successful in the past. So it was a worthwhile thing to. I'll be looking for a more environmentally friendly block to use for that type of uh, scenario to hold that in place. And once I got a few cross members in place, I was able to remove that and then build the rest of the structure around that. You'll notice at this point that my bridge has basically this long space across the top and a few trusses going out the sides. That is not the bridge that I ended up with. And so let me change gears once again. This is kind of where this is like watching a Julia Childs show where she all of a sudden has pulls the completed dish out of the oven that has been sitting there for a while. So I have take my truss away and bring out my finished cake, if you will, and set that up here. And we can see here's my current structure has a few more members involved in it. And the reason for that is that I tested it, and in addition to figuring out that it wasn't quite level and I needed to do something about that, it also, whoops, there we go. Get that turned around correctly. It also became clear that I had not supported the area where the force was going to be applied. And that was like, made me wonder what I was thinking about when I made my first design. So I had fully intended to load it from the center, and then here I went and designed it so it didn't have any real strength other than just a beam there. So I went back and redesigned it and came up with this design. Uh, and I'm just kind of curious as to what this is going to do. So let me go ahead and click done there. Start a new experiment. And here, this is going to set up with both force and displacement. So we can take a look at the amount of deflection that I get here, as well as the force being applied. And I'm curious as to how well my bridge is going to fare in this live demonstration. Oh, something obviously is, oh, heard a snap where, oh, basically what's happening is that top end is bending over. So that's pretty much my failure point there. So I'll just let it go. So now this was a bit more destructive than I might have hoped for, but let me just take the bridge off for a second and talk a little bit about that. Take the hardware off, the bridge off, and I'll bring that other camera view back for a second just so we can evaluate this. So see where my view is. If I look at what actually broke, it's all pretty solid still, but it was definitely bending kind of sideways here. So, and I can see like right here, there's a member that I built in here that is a little bit sideways. There's a fracture on this one as well. I could actually go back and rebuild those. The structure is largely intact, but those are some weak points that I could kind of redesign and figure out how to make them stronger. The whole bridge is largely intact. I don't have to go back and spend another week building a new bridge. I can actually just go back and take some time to maybe break off the pieces that are failing, figure out how to redesign them, or if I need a different structure altogether in there. So that's my opportunity to go back and apply that engineering design process. So let's talk about that a little bit. First of all, before I jump off of this screen, I note that stress testing is really helpful. So just putting a little bit of force on my bridge, let me know, okay, this is not symmetrical, this way I need to shore it up. Or I completely, when I applied a force just to the top of the bridge, it became clear that I was just dealing with a beam that was going to break until I provided some additional structural supports there. So it doesn't have to be destructive testing. It can be just a little bit of force to see where things are going. I know some instructors have had their students break their bridge multiple times, and with the structures materials tester, you can do that without destroying the entire bridge. And figure out where the weak points are and redesign and rebuild them. And that really gets to this engineering design process. I always like to remember this very short version of it: plan, do, check, act. So, design your solution up front, build it, and then check it, see how it's working. So that's the testing part. And then refine and revise your solution. And it's a cycle. There's a lot of different versions out there. There's some with 7 steps, some with a dozen steps or more. They all kind of follow the same basic pattern though. So, and I can remember 4 things. I can't remember 12, unfortunately. So plan, do, check, act. And so right now I'm at this act stage where I need to revise my solution and try again. I've been showing you the GoDirect Structures and Materials Tester. It comes with this Beams to Bridges ebook, which you can also purchase separately. And the first thing I showed you was the truss testing accessory, this item right here. Just mounts on the back of the structures tester and allows you to test single width trusses. Going forward, just circling back to look at your questions here. There were several questions about, are there other options besides the structures and materials tester? And of course there are. When I did this in my classroom, the structures and materials tester hadn't been developed yet. So I, like a lot of teachers, pushed 2 lab tables fairly close together and centered that bridge between those 2 lab tables and hung a bucket over from the bridge with some sort of a fixture on top. And then had students just put masses from my weight system into the bucket until it failed. Now, the downside of that is that failure was catastrophic. It was really fun and exciting, but there was no re-engineering. There was they just took their splinters and went home pretty much. So that is the kind of the low cost option. And then you're just counting, how much weight you put into the bucket to see how effective it was. Certainly a lot of fun. Students still enjoyed it. Probably not as able to pull some of those engineering design elements out as you might be able to with the more refined measurement tool. Another option that we've promoted in the past is to make some sort of a device like this where you can mount your bridge on that. And you just place this on a force plate and then have some sort of a means of loading up your bridge on top here with some sort of a plate and weights or bricks or books or whatever the appropriate material is that you have in hand. And then you can just use the force plate to determine how much weight was applied to the bridge before it failed. And then if you were to do that, I'd recommend zeroing the force plate value before you start adding weight to the top of the structure, so you can get an accurate value of how much the bridge actually held. Our force sensor, it maxes out at 50 newtons. It certainly is appropriate for single trusses of light material, but for testing bridges, it's really not a significant enough force to work for a bridge competition. So unless you had a significant lever arm setup, it's probably not the best option for testing bridges. Talked a little bit about gluing joints. One of the things I did was when I started working on adding members, I would clamp them with just these small clamps, or I used painter's tape to kind of apply some stress to keep wood in contact with itself, with the 2 parts that were being glued together. That helped quite a bit in making sure I had good gluing for my joints. And again, gussets are another option. And when possible, use a butt joint versus a lap joint. There were a few questions about other uses for the structures and materials tester, and we've certainly used it for testing certain Science Olympiad activities, like they have a tower activity and a boom lever activity. It takes a little bit of constructing structures on top to be able to accommodate those, but it is possible to use use the structures tester for those activities. We had a professor in Stanford use the structures and materials tester for testing brittle material. They used chalk, and they did a couple of different tests with that. And there's a link there in the handouts for access to that activity. It's a really nice, nicely developed activity. We had a student who was actually creating their own poly material, like a saran wrap type of material. And we helped them develop a set of jaws that would hold that material so that they could stretch it and test the strength and other properties of that material. And again, those are links that you can find to pages of interest on our website. We've had some questions about biomedical applications, and that's a yet to be developed area. So if you come up with ideas for that, that'd be great. Let's see. I'm looking for crowdsourced tips over here. Let me look in the chat and see what else is going on here. It looks like glue for spaghetti. Again, I don't have much experience working with popsicle bridges or spaghetti bridges. So I'm a little flat earth when it comes to providing any suggestions around that. If anybody online has suggestions, otherwise I'll do a little bit of research and I'll put some information out to the people who participated in the webinar today. When I'm building bridges with basswood or balsa wood, especially with basswood, I just use a wood glue. Sometimes wetting the surface can be helpful to get that glue to adhere evenly to the surface of the wood. I have a note here that clothespins work well as clamps too. That's great. The key is just to get those two pieces of wood in contact with each other with the glue in between them. Hot glue works great with balsa wood. It's a really strong bond, but hot glue will tend to not be as strong a bond on basswood, or potentially like popsicle sticks would be a harder wood. It doesn't make as strong a bond, and you may find that the glue is actually failing. And with hot glue, you can get kind of a thick bond, but when I'm using balsa wood, it's just a really nice, quick way to make structures. So like when I build trusses just for the truss activity, I'll use hot glue, and you can put these together. They dry that quick. They're ready to use. You could make a series of trusses and test them, certainly within a class period, depending on how many students you had working through your tester. Oh, mini marshmallows as joints for spaghetti bridges. That's interesting. If you're using a 1/4-inch wood, like balsa, what's a good span length for kids? If we're talking about bridges for 1/4-inch balsa, probably, our structures tester is set up for, it can span about 45 centimeters, roughly, right in there. And I would say we typically run right around 30 a lot of the bridge competitions seem to have a limit between like 30 and 40 centimeters. So that's probably a good target. Quarter-inch wood can be pretty strong, so you probably wouldn't want to go any shorter than that, else you're going to have a difficult time actually breaking the bridges with a reasonable amount of force. Again, I'll put out a plea for any information you guys might have about tips for spaghetti or popsicle bridges. Again, there's a lot of information online. If you just Google that, you'll get a lot of tips, a lot of different websites out there to provide resources. And there was a question about scaling bridge activities from like elementary school to middle school to high school. My comfort level is definitely at the high school level, but if people have suggestions for maybe that marshmallows as joints for a spaghetti bridge is great for elementary, where they maybe don't have dexterity for great gluing activities, and minimize some of the mess by just having temporary joints put together with some marshmallows, although they may be tempted to eat their joint material, and I'm not sure about that. I think that's about all I have. Dylan, is there anything else coming through in chat that we need to address?
No, I think that we got to everything. Yeah, some good tips in here. You might have read this already, but some simple activities: use mini marshmallows as joints for spaghetti bridges, which I think is really interesting.
Mhm.
Um, yeah. Let's see. Somebody says, I've done this with a physics class where they were able to choose their materials and a cost factor was involved. Oh, and that
Yeah,
looks like, yeah.
that's an excellent extension into, kind of another aspect of engineering design is you have to be, you're constrained by your budget as well as the materials that you're working with and the design features. That's a great tip. Well, I think that's going to wrap us up unless there's any last minute questions. And if you have questions, you can always email engineering@vernier.com. And let me know what questions you might have out there. We'll be glad to get back to you in short order.
And we have a fun tip from Kirk, who let us know if you search for International Bridge Building Competition, you can see their yearly rules. They always have a 30-centimeter gap that needs to be spanned. Also, Science Olympiad often does bridges, but this year it is towers. So just a fun piece of advice from one of our viewers. And I
Excellent.
did drop a survey link in the chat. If anyone is still with us and wants to give us some feedback on this webinar, we would love to hear from you. And we'll probably leave it open for just a moment more to see if we left anyone's questions out or anything. We are here to help y'all. Everyone, you can email us at engineering@vernier.com if we didn't get to you. We'd love to answer your question. And with that, I'll go ahead and end the webinar. Thanks, everybody.